In the previous lectures, we discussed about the power dividers and directional couplers. In this lecture, we discuss microwave filters. An ideal filter provides perfect transmission for all frequencies in certain passband region and infinite attenuation in stopband region. Typical filter responses, different types of filter responses are low pass. So, in a low pass filter, signals between 0 and some upper limit of frequency are transmitted and all frequencies above the cutoff frequency, they are attenuated. Another response is high pass response, and a high pass filter transmits all frequencies above some lower cutoff frequency and attenuates all frequencies below the cutoff frequency. A band pass filter transmits all frequencies within a range of two frequencies, omega 1 and omega 2, and attenuates all frequencies outside this range. And a band reject filter attenuates signals over a band of frequencies. So, a filter characteristics can belong to any of these typical responses, either low pass, high pass, band pass or band reject. Filter design problem at microwave frequencies where distributed parameters are required to be used is quite complicated. Two commonly used low frequency filter synthesis techniques are image parameter method. In this approach, filter with required passband and stopband characteristics can be synthesized, but without exact frequency characteristics over each region. Another approach of designing filter is by insertion loss method, which provides a systematic way to synthesize the desired response with a higher degree of control over the passband and stopband amplitude and phase characteristics. In our discussion, we will consider the insertion loss method. Some of the design trade-offs for microwave filter synthesis using the insertion loss method are: a binomial response is used when obtaining a minimum insertion loss is the priority. So, we go for a binomial response when we would like to have minimum insertion loss. A Chebyshev response satisfies the requirement of sharp cutoff. That means, filter response beyond the cutoff frequency, if it is to fall very sharply, then we go for Chebyshev response. A linear phase filter design is used in cases where the attenuation rate can be sacrificed for a better phase response. We will see that a binomial response or a Chebyshev response, we essentially specify the magnitude response of the filter. Whenever we require some specified phase response, the attenuation rate can be sacrificed and a linear phase filter design methodology can be adopted. Now, we introduce one parameter which is called power loss ratio. The power loss ratio in a filter network we can define as PLR is equal to power available from the source divided by power delivered to the load, and therefore, it can be written as P in by P load, which is equal to 1 by 1 minus mod gamma omega square, because we know that P load is P in into 1 minus mod gamma omega square, and insertion loss in dV is given by IL is equal to 10 log PLR. Since magnitude of gamma omega square is an even function of omega, we can express gamma omega square as a polynomial in omega square, and magnitude of gamma omega square can be written as m of omega square divided by m of omega square plus n of omega square, where we have this m and n are real polynomials in omega square, and therefore, PLR, the power loss ratio, it becomes 1 by 1 minus m of omega square divided by m omega square plus n omega square, and this can be written as m omega square plus n omega square divided by n omega square, and finally, PLR is equal to 1 plus m omega square divided by n omega square. Now, this power loss ratio we have written in the form of polynomials in omega square m and n. Now, let us see some practical filter responses. The first one we consider, it is called a maximally flat filter. Such filters are known as binomial or Butterworth filter, and for a low pass filter the power loss ratio is specified as PLR is equal to 1 plus k square into omega by omega c raised to the power 2 n. Here capital N is the order of the filter and omega c is the cutoff frequency. So, at omega equal to omega c, PLR value becomes 1 plus k square. When omega is larger than omega c, attenuation increases monotonically with frequency. As frequency is increased, the attenuation increases, and when omega is very large compared to omega c, we can approximate PLR to be equal to k square omega by omega c raised to the power 2 n, and therefore, the insertion loss increases at the rate 20 n dB per decade. When omega is much larger compared to omega c. So, 20 n dB per decade means as the frequency changes, frequency becomes 10 times larger, the attenuation increases by 20 n dB, n is the order of the filter. Another response which is used in design of filters is equiripple. Such filter response is also known as Chebyshev response, and for a low pass filter power loss ratio is given by PLR is equal to 1 plus k square T n square omega by omega c. Now, this T n, these are Chebyshev polynomial, and for omega less than omega c, T n will oscillate between plus minus 1. The passband response has ripple of amplitude 1 plus k square. For omega much larger than omega c, T n square omega by omega c, this becomes approximately half 2 omega by omega c raised to the power 2 n, and PLR becomes k square by 4 2 omega by omega c raised to the power 2 n. So, here also insertion loss increases at the rate of 20 n dB per decade, but the insertion loss in Chebyshev response is greater by a factor 2 to the power 2 n by 4 than binomial response at omega much larger compared to omega c. So, this is shown here for filter order of 3. Here we can see that y axis is the power loss ratio PLR. Now, for a maximally flat filter at omega by omega c equal to 1, it becomes 1 plus k square. Also for the equiripple case also, at this passband edge it becomes 1 plus k square, but here we see oscillation within the passband, whereas a maximally flat filter increases, the power loss ratio increases very gradually, and after the passband edge, that means for omega by omega c greater than 1, we find that the attenuation becomes much sharper or steeper for equiripple response as compared to maximally flat. We talked about linear phase, although we will not discuss this in detail. For some applications, a linear phase response is desired in the passband, and a linear phase response can be achieved using the phase response given by phi omega is equal to a omega 1 plus p omega by omega c raised to the power 2 n. Here phi omega is the phase of the voltage transfer function of the filter and p is a constant. We define one parameter which is group delay, tau d is equal to d phi by d omega, and if we find out d phi by d omega from this expression, then tau d becomes a into 1 plus p 2 n plus 1 omega by omega c raised to the power 2 n. Group delay thus becomes maximally flat response, and in a linear phase filter the phase distortion will be kept under control while designing the filter. The steps involved in filter design by insertion loss method are: we start with some filter specification. In filter specification, we specify the cutoff frequency, if it is a low pass or a high pass filter. We specify the frequencies of the pass band edges for a band pass filter, and also we specify outside the pass band how the insertion loss will happen, and we will see that insertion loss specification outside the pass band at some frequency, this information will be used in designing the order of the filter. So, once we have the filter specification, we know the order of the filter that would be needed. We go for a low pass prototype design, and for that prototype design we can find out the parameters of the prototype filter. This prototype is a low pass filter with unity cutoff frequency. The source resistance is normalized to unity, and the load impedance also in many cases is normalized to unity. So, therefore, after finding the prototype filter, we need to do scaling. We need to scale the cutoff frequency of the filter to its actual cutoff frequency value, and once we do the scaling, the reactive elements, inductor and capacitor values calculated from the low pass prototype, they will change. Similarly, we need to do impedance scaling, because our source resistance in the prototype is unity. So, once we do all such scaling, and then depending upon the type of the filter we intend to design, we can also perform transformation from low pass to high pass, low pass to band pass, from low pass to band reject. After this comes the actual implementation phase. In this implementation phase, we need to decide how we are going to implement the filter. It may be using lumped element, it may be using transmission line sections, maybe microstrip lines, or it may be using waveguides. So, this implementation of the design filters, it is quite involved, and we will not attempt it here. To get an idea how we go ahead with the design of the low pass filter prototype, let us consider a circuit shown in the figure. Here the source has a impedance of 1 ohm, and let us consider the cutoff frequency to be 1 radian per second, and it essentially represents a second order filter where we have this element L, series element L, and shunt element C, and this filter is connected to a load resistance R. So, for a second order filter, when the cutoff frequency is 1, in that case PLR becomes equal to 1 plus omega to the power 4. For this circuit shown here, Zin can be found j omega L, the reactance, in series with parallel combination of R and C, which is given here, and also once we have Zin, the gamma looking into this network, since our source impedance is normalized to unity, so gamma will be Zin minus 1 divided by Zin plus 1. And therefore, we can write PLR, which is equal to 1 by 1 minus mod gamma square, and here we can substitute gamma into gamma conjugate, and finally it will become mod of Zin plus 1 whole square divided by 2 Zin plus Zin conjugate. Now, if we substitute the expressions for Zin and Zin conjugate, we get Zin plus Zin conjugate is equal to 2 R divided by 1 plus omega square R square C square. And mod of Zin plus 1 square can also be evaluated by substituting the expression for Zin and it comes out to be R divided by 1 plus omega square R square C square plus 1 whole square plus omega L minus omega R square C divided by 1 plus omega square r square c square whole square. So, with mod z in plus 1 square calculated and also z in plus z in conjugate calculated, once we substitute these two terms, we get the expression for PLR, which is shown here. It is 1 plus omega square r square c square divided by 4 r into r by 1 plus omega square r square c square plus 1 whole square plus omega L minus omega r square c divided by 1 plus omega square r square c square whole square. Now, this can be further simplified and put in the form as shown. So, the PLR is expressed in the form shown here. We know that PLR is a even polynomial in omega square, and we saw that in our case when n is equal to 2, it is 1 plus omega to the power 4. So, we can write it in this form, and now if we make a term by term comparison, because here for the expression for PLR we have omega square, we have actually 1 plus 1 by 4 r 1 minus r whole square, and then a term which is the coefficient of omega square, and another term L square r square c square divided by 4 r, which will be the coefficient of omega to the power 4. So, we can equate them, and therefore, this term has to be equal to 1, which implies that 1 minus r has to be equal to 0 and r equal to 1, because then only we get this term to be equal to 1. So, our load resistance is r equal to 1. The other term when r equal to 1, we get c square plus L square minus 2 L c equal to 0, and therefore, L minus c whole square becomes 0, which implies L equal to c. The last term L square r square c square by 4 r, this become 1, and since r is equal to 1, we get L square c square by 4 equal to 1, and we have seen L equal to c. So, we can solve for L equal to c equal to root 2. So, we can see that by comparing the expression for the PLR obtained from the prototype circuit with that of the PLR for a binomial response, we can calculate R, we can calculate L and C, and this we have carried out for a filter order 2, n equal to 2, second order filter. Now, this can be done for a generic low pass prototype, where we have the prototype, this prototype, here we have R naught equal to G naught equal to 1, then it begins with a shunt element, then we have a series element, another shunt element. So, we have this ladder network, and finally, G n plus 1, this is the load. And when the prototype begins with a series element, we can draw it as shown, and here also, if required, we can represent it in terms of a current source and a parallel source resistance. So, these are the two commonly used prototypes for which the tabulated values for these G's, that means G can be either C or L depending upon the prototype. It can be a series element or it can be a shunt element, and the values of these G's are tabulated. So, this table shows the element values for a maximally flat low pass filter prototype with G naught equal to 1, omega c equal to 1. And we can see that we found out in our second order filter L equal to C equal to root 2, which is 1.4142, and R equal to 1. So, G 3 is equal to 1. So, essentially we solved by our prototype circuit this row of the table. So, for other values of n, we can directly use these values for series and shunt elements, that means the G's from this table. Here we are showing up to filter order 5, but values are also available for higher order filter. Now, in a practical filter, it will be necessary to determine the order of the filter, and as already mentioned, that usually it is dictated by the specification on the insertion loss at some frequency in the stop band of the filter. Suppose at 1.5 times the cutoff frequency, we want an insertion loss of 20 dB. So, from this type of specification, we can determine what order n is required, and once we can know n, then we can choose these values G 1, G 2 up to G n plus 1 from the table, and then we can find out the corresponding values for the inductors and capacitances for providing the desired cutoff frequency, and also when the source resistance is scaled to the desired value of the source resistance. So, let us see what do we mean by this impedance and frequency scaling. The prototype filter has R s equal to 1 omega c equal to 1, and also for maximally flat response we have seen that R L equal to 1. A source resistance of R naught can be obtained by multiplying all the impedances. Please note that this L and C, they will provide impedance values omega L 1 by omega C, and if we multiply the impedance values provided by the elements in the prototype design by R naught, then essentially we get the solution for those inductors and capacitors when the source resistance is R naught instead of 1. But still our cutoff frequency is 1. So, next what we do? We change the cutoff frequency from unity to the actual cutoff frequency omega c for a low pass filter. So, if we do that, we require to scale the frequency dependence of the filter, and this is accomplished by replacing omega by omega c. So, if we do both impedance and frequency scaling, then the scaled values of the inductance become R naught L k by omega c. So, this is the series element we used, and scaled value of the capacitance C k becomes C k by R naught omega c. And with the impedance scaling, the scaled value of the source and load resistances now become R naught and R naught R L. So, if our original prototype we have G n plus 1 as 1, that means R L equal to 1, then now new value will be R naught into 1 equal to 1. So, let us see how we utilize these concepts in designing a low pass filter, and that will actually clarify whatever we have discussed so far. So, we consider the example of design of a low pass Butterworth filter. So, let us consider a maximally flat filter that has cutoff frequency of 2 gigahertz, and the filter provides at least 15 dB attenuation at 4 gigahertz. The source and load impedances are 50 ohm. So, first thing we need to do is to determine the order of the filter. So, from the expression for PLR, we have seen that at an angular frequency omega, the attenuation of the filter in dB is 10 log 10 1 plus omega by omega c raised to the power 2 n. So, this is the attenuation of the filter, and therefore, in our case omega c is 2 gigahertz, and we want 15 dB attenuation at 4 gigahertz. So, we can write 15 by 10, which is 1.5, is equal to log of 1 plus omega by omega c become 2. So, 2 to the power 2 n. If we solve for capital N, we get n is equal to 2.47, and therefore, we use n equal to 3, that means a third order filter. And the table which we have just discussed, from there we see that G 1 is equal to 1, G 2 equal to 2 and G 3 equal to 1 for a third order filter. And therefore, we can draw the circuit of the filter with 50 ohm source resistance and 50 ohm load resistance, and by applying frequency and impedance scaling, we can find out C 1 to be equal to 1.5915 pf. So, the shunt capacitor, first capacitor is, and L 2 the series inductance, it is 7.9577 nanohenry, and since we have G 1 equal to 1 equal to G 3, C 3 the next shunt capacitor is also 1.5915 pf. So, this completes the design of the filter, determining the values of inductances and capacitances that would be required to get an attenuation of 15 dB, at least 15 dB at 4 gigahertz. Now, how do we realize these capacitor and inductor values? That comes under implementation. So, we have seen how we can design maximally flat low pass filters. In the next lecture, we will discuss how we can design equiripple filters and the procedures involved in designing the prototype equiripple filters. Once the low pass filter prototypes are designed, then depending upon the requirement, if we want a high pass filter, we need to perform low pass to high pass transformation. Similarly, low pass to band pass or band stop transformation. So, in our next lecture, we will see how these transformations are performed.